Let's look into de Bruijn graphs. So de Bruijn graph is another approach. We have talked about OLC. So we'll look into this topic in different these following steps. Just stay with me. So this approach is used for Solexa and solid platforms, and they generate overlapping substrings of length k from the reads. So what we do here is we are not taking those reads. We are actually subsetting those reads. We are looking into, for example, if the read is 30 base pairs, we can divide into, for example, our k-mer size is 3, so we can divide into 10 different segments starting from position number 1. Same way we can do the same thing with position number 2 and position number 3. So in this way we will have a huge number of those k-mers. So that's where the complexity of this algorithm is. What we do next is we generate the de Bruijn graphs where our nodes are these k-mers, and which are actually the fixed length strings or k-mers, and edges they represents the overlaps of k minus 1 nucleotide. So one k-mer should be matching to another one with k minus 1 length. So for example, if the k-mer size is 3, at least 2 of them or I would say at most 2 of them, they should be overlapping with one another, not the third one. So 2 nodes are linked with an edge if they share a k minus 1 mer, and then we connect one k-mer to another if the 2 k-mers completely overlap except for one nucleotide at each end. If they completely overlap, we will merge them together. Then within that graph which we have formulated, we'll try to find a Euler cycle. As we have seen earlier, it's where we are visiting each edge of the graph exactly one time. So here is an example. We take a sequence. For example, the read is of size 4, ATGT, and we can have 2 possible scenarios. So we can have ATG. So our k size is actually 3 in this example. So k is equal to 3, and we can have these 2 k-mers, these 2 from this one, and from third one we can have this one. When we put them together, so we have AT from the first one, these 2 they overlap, T and G, with the second one, and we can have among us these k-mers which are coming from the second read. Here is the overlap, and this is from the third one. When we put them together in a network, all of them, we can have something like this. So we can have this AT, and then we have this situation where we have TG. We can merge these 2, obviously. We can merge here, we can merge here. So in the middle we have TGs, and we can have different routes. So we can have something like this, and something like this, and something like this. So we can get a consensus out of it. Different DBG or de Bruijn graph assemblers which are there. One is Euler, one is Velvet, Allpath, Ibis, SOAP de novo. So these are some of them which are frequently used in the genome assemblies. You might find them in literature, guys, these assemblers, since they are dealing with your solid or Illumina Solexa data. So that's why they are there. They work best for short reads. There is no pairwise overlap computation and efficient algorithm, because rather than comparing those reads in terms of pairs, breaking them into those small k-mers or small fragments, and in the end it's merging those fragments together. So it's kind of efficient, and this approach is most widely applied to short reads from Solexa and solid platforms.